40 yaşında ağır olmuş ve onları sonucu 10 bir fazla.
I'm starting my last lesson. So, our equation of motion was given with this equality. Equal to the inertial mass. There were two different, similar but different examples. First one was the defining gravitational force. It was like this. Issue. So, here, I'd like to write. These are all in 3 dimensions, okay? Geometry is various group is yellow. They are constructed of yellow transform issues. Okay. So they have similarities, but there are delicate differences. So I would like to pinpoint on those aspects of these two field theories. So here, maybe. So there is a spherical symmetric distribution of matter with total mass. This is the active gravitational mass in the context of defining gravitation, okay? And maybe it will contain some amount of charge. Okay? So we have a particle here. For example, it's the image of this curve is given as this in this shape. Okay, this is the point. This is the vector at that point. Okay. So we have M, which also is equal to energy in special relativity and general relativity. We have inertial mass is equal to the gravitational charge of the point particle, okay, is the passive gravitational mass. It can have angular momentum, but since this configuration is spherical symmetric, it's not spinning. Because if a sphere starts to spin, it is not a sphere anymore, okay? Because it has axial symmetry. Cylindricals. Okay? So the point particles may have a spin in classical sense. Okay. That's the relativity. Okay. The electric charge, and this is the electrical charge on our point particle. It's massive. So this source may have momentum, but it is proportional to its velocity, okay? So the test particle will have momentum and it's related to its velocity. So, these are not arbitrary, okay? This is not, this is, or its momentum, this is determined by the source, okay? So this M could be very large. For example, this spherical distribution is contained in a ball of radius, let's say, R, okay? So it is also a parameter. It's also a parameter of our problem. It could be very large or very small. There's no limit in non-relativistic classical physics for these things, okay? These quantities. But I'm going to talk first mainly on the situation that this N could be very large. This Q could be very large. So when our particle is very near to the source, when it is at the vicinity of that source, it will instantaneously, for the charge case I'm talking, it will accelerate and it will reach to a velocity that has speed very close to the speed of light in vacuum. So there will occur relativistic effects, okay? Now, I want to ignore that at the beginning. So if M is large, and this thing is the point particle is very near at the vicinity of the source, so the fields will be very huge, very strong. And again, the same situation will occur. So I'm neglecting these and taking my point particle enough far away from the source. Now I can talk about Galilean covariant relativistic mechanics. Galilean relativistic mechanics, non-relativistic mechanics. So I know that this part, the right-hand side, it is only related to the geometry, and there's a parameter with the inertial mass. Okay, right-hand side is kinematical part of the Newton's second law. Left-hand side will be determined by experiments. We know the form of this these force laws. In the case of gravitation, it's like this. In the case of electromagnetism, it's like this. But one may think that this is a Lorentzian force. It's called Coulomb Lorentz force, but it is not Lorentzian. It should be Galilean coordinates in order to fit this equation. Otherwise, you can't do anything. Let me extract it a little bit more. Sorry. Okay. You know that, let's say the source has no momentum, so its velocity in an inertial frame, it's 0. So this particle is far away from the source, so its magnitude, the magnitude of its velocity is called speed. Speed is low enough to solve this equation. You can do it. Note that this A is like this. AI dxr. It's a one form in our Newtonian space. Here B is like this. B1, Bx2 wedge, Bx3, and cyclic permutation. So there are 2 more terms. So this is an element of the sections of the 2-form bundle over 3-dimensional 3D space, coordinate Newtonian space. Now, in R3, we have vector product, okay, and also dot product. This dot product is its leading metric. From physical side, we call it metric, but the mathematicians call it the scale product or even. We also have, this is a very special structure belonging to 3 dimensions. I mentioned this before. So there is R3, there is wedge product, and Hodgson, Dr. Özgür taught you that is previous lecture. Now, you know that in our 3-dimensional formulation here, let's see, these are vector fields. These are vector fields, so they belong to the sections of the tangent bundle of R3. Okay? But this is a one form. So you can take its magic tool. This will give this, they are equal. They are equal, they are identical. Okay? But what about this? What's the relation of this 2-form, magnetic 2-form, with the magnetic vector field? Remember that we are in 3 dimensions and everything is moving slowly with respect to the speed of light in vacuum, okay? So B is a 2-form. Okay. When you take its first rule, it's a 1-form. When you take its metric rule, it's a vector field. So this is the power. Again, I'm underlining the fact that we are in 3-dimensional, non-relativistic region. Okay? Here, there's no problem. at first. I will talk about this case later on. Let's only concentrate on the electromagnetism part. Example. Okay. So you know that we can, as Galilean observers are also associated with curves in this setup, in modern differential geometry formulation of classical physics. Okay. So let's say there's a Galilean observer observing the motion of the point particle, which has inertial mass m and electrical charge q. They are all reference frame independent motions, remember that. Okay. So this Galilean observer should be identified with a, let's say, a curve C prime or C bar, let's say. Since this point particle is exhibiting Galilean motion, it's not Lorentzian. It's very far away from the speed of light in motion. We can make this, okay? For every Newtonian instant, we can make we can realize this equality. What does this mean? The Galilean observer can see himself or herself as seeing the particle as being at rest. Okay? He can sit on the particle in Galilean regime. But remember, if I move this particle very closely to the source and the charge is very huge, and then I leave it to the hands of the source, it will accelerate immediately and will reach the speed of light. Okay? So you know that. First of all, I'd like to say that we are talking about test particles. What does it mean? I am trying to understand the motion of a point charge massive particle in two respects, from gravitational point of view and electromagnetic point of view. Okay, when it is near the source, test particles do not change the configuration of the field. Okay, that's the definition of a test particle or a test field. You may say maybe when you are dealing with field theories. So here is our spherical symmetric source. It has mass and charge. Our test particle has also inertial mass. It's equal to the passive gravitational mass itself, and it also carries an electrical charge. Okay, but test particle means it has no Faraday lines. Okay, Faraday who is responsible for bringing the field concept into physics. A very, very intuitive business. Both in gravitational respects and both in electromagnetic respects, the charge does not have any Faraday lines. So it is a test particle. But note that this test particle is making motion with respect to the source. So there is relativity here. I know that. So this has Faraday lines. They are active Faraday lines. They are acting on to the point particle. So the situation is like this. From the electrical point of view, you may say this is positive charge. So these are spherical symmetric Faraday lines. Okay. there's nothing interesting. But when this particle is near the source, at the vicinity of the source, it will immediately accelerate and will gain very, very high speed. This is the magnitude, and it's nearly equal to the speed of light. It's below this number. Okay? But note that we can sit on it, not as Galilean observers, but as Lorentzian observers, because its speed is nearly equal, but lower. Okay, lower than the speed of light. We can sit on it, then this will move. When this starts to move, we know from our experiments in the laboratory that the electric field lines will, these parallel lines will not be spherical symmetrically distributed anymore. So this will be the case. So the energy of the field will concentrate to the transverse direction. This will happen. Everyone knows. Okay. So relativistic effects will occur here. And again, when you sit on the source, these lines will pass through the point part. So again, neglect its parallel lines. How can we do that? We should see that we are not Galilean observers anymore. We are Lorentzian observers. Note that the source is at rest, but the particle is exhibiting relativistic motion. So this equation will not be valid anymore. This is very important. And this argument is not a good argument. I'm doing this with you. You cannot find these things in any book. Okay. So we should be careful when we are talking about this. In the gravitational case, if our test particle with passive gravitational mass mu is equal to the inertial gravitational mass, inertial mass m, it's very near the source, and the source is very massive, then it will accelerate, and it will have a speed near the speed of light. Okay. But it needs us to rise up this to the total mass of the source. But it has a radius. Okay. We know from Einstein's general relativity that after a while, if you fix this and rise this, this will be below the Schwarzschild radius of this source. And non-relativistic gravitational theory will broken. Okay, it will not work anymore. Okay. So this was very important. The things that I have tried to emphasize. Let's just only pass to the Maxwellian electrodynamics. So here, the electrodynamics is not Maxwellian, it's Galilean. So it's a Wigner contraction of the Maxwellian theory in some sense. Okay. So, in our three-dimensional picture, we have fields. The electromagnetic field is described by the pair of these vector fields. They are also parameterized with Newtonian time. Yeah. If and only our particles, as particles, exhibit motions with velocities that have very, very much less magnitude than the speed of light. So we have here an Euclidean metric. I will denote it by a hat. I will put a hat on it because in the four-dimensional case, I will use G for denoting line symmetry. Okay. So we have coordinates here. T is a time. T is a parameter, and we have Cartesian coordinates here. X1, X2. These are coordinates. So I put a semicolon in order to separate this parameter from the coordinates. Okay. These are due to Faraday. Monster. And the calculus is based on Gibson data. Still that, now I put a hat in order to give meaning to this hat. I'm carrying this here because it's the metric dual of the one home field E with respect to the G hat metric plus A T dot B tilde. I also will put here, no, I'm not going to. I will just mention that C takes an interval of non-closed or semi-closed interval and maps the parameter or this interval to three-dimensional Euclidean space, which is the space of non-relativistic Newtonian. So now we can formulate changing the formulation. And changing the physics. In what sense? This is the regime of Galilean relativity. This will be the regime of Lorentzian relativity. So we have four-dimensional inner control space-time. So we have again E and B, but they are different from the E and B's I have written before because they are living in four dimensions, not in three dimensions. But I am using the same methods. Be careful about what I'm saying, okay? So there will be a metric. Now E is again like a one point, but it isn't. Because it's not it does not have any time component in anything. It can have, but it will not behave as a one form in anything. Because it is a one form in one inertial reference frame, it will always be as it is. Now B is also like this, B1, Bx1, Bx2, which Bx3 plus B2, Bx3, which Bx1 plus B3, Bx1, which Bx2. Now, note that these are Hartmann derivatives, but belonging to the differential structure of a four-dimensional manifold, not a three-dimensional manifold anymore. So, in 3 dimensions, I have things like this. There's also a chart here. It is denoted by C. This is the speed of light in vacuum, Ct, x1, x2, x3. But it is a coordinate. It is not a coordinate. This is very important again. And we are using the same Cartesian coordinates for this construction. It's more adapted to this problem. Here it was A, AI, AXI. But this D belongs to the differential structure of R3, maximal atlas, maximal atlas of R3. But this D, those D's, all belong or related with, you may say, in a more real sense, to the atlas of maximal atlas, four-dimensional manifolds. So there is only one differential structure in 3 dimensions. There could be many more, but we use the standard form because it is very convenient for our calculations, which are in equilibrium experiments. These notions are very important. Now, so there should also be a force law here. We don't know what will it be, but it should be like this, okay? F, but I'm not putting a vector here, but it's a vector. Okay? It will be a metric 12 with respect to the G. G will be like this, minus T squared, dt, cancel product, dt, plus G hat. Okay? So, what we are doing here is, we are in the relativistic regime. We are working on a manifold, and our manifold, when we are doing physics on manifolds, the coordinate systems will have no meaning. But we are at an inertial chart, so there is an associated coordinate system here. But it is not important, because our physics now is Lorentz covariant, so we can pass to any coordinate system, actively or passively, it doesn't matter. So we can use active diffeomorphism, passive diffeomorphism, it does not matter. So this is a Lorentzian metric with signature in my convention. It is 3 plus and 1 minus sign. When you represent this thing as a matrix in the adaptive coordinates, so this is adaptive coordinates are the Cartesian ones, as I told you before. So this is the relativist point of view. So Q doesn't change, but E is different, and this tilde is different because this has hats, but this does not contain a hat. So there is a velocity field, but I am denoting it with another map for a relativistic curve. Okay? This curve was not relativistic. But when you bring the test particle to the source, this will be related to a relativistic curve, but it's special. That's shape. Okay? We should be very careful when we visit. So this is a true form, but note that we are in 4 dimensions now. When you take its hot star, you will get a true form. So it will not be directly related to this. This is also very such that there is a question mark here. When we is near the speed of light, we're working, this is C, and this is our curve, okay? But it has special indices. Here we have gamma, it is like that. Zero and gamma I. In this regime, it should be, it should satisfy this condition. So what we have done here is we used our knowledge about physics and tried to move in a logical way. Try to set up something. But I will. Kaç dakika olacak?
15.
Tamam, bitireyim. So these things in 4 dimensions are with G. Then we do not scale with. This is my notation, 4 dimension equals this case. But mathematicians sometimes use this P1 with its signature, or 4 dimension with 1 minus sign in the signature. So these are notations. Now, these do not behave like one form. Electric part is not a one form in 4 dimensions. B is like a 2 form, but it is not. Because they do not have any individual reality anymore. There is no space in relativistic physics. There is no time, whereas selected ones are not existent. There are many spaces, and many times in relativistic physics, in special relativity, and also in general relativity, local units. But we can make this. We also have T, it's a new coordinate now, we have to use it. When you take its Cartan derivative, it's like a one. It is a one form in the sense it is an element of the co-basis defined with respect to the Cartesian coordinates, okay? So let's take CS1. No. We define a thing called F. This is the Maxwell two-form. EP, wedge, E. This is like a two-form, but not a two-form. This is one of the co-base elements plus a two-form. Now this is a two-form. Maybe I should write E is an element of the bound form field. But let's put, because they are not by themselves a bound form, and also for B. B is an element, or maybe we can put here. There are no. But there were sources, rho and G. This is the electric density. This is the electrical charge density, the electrical current density, as everybody knows. Now I define a capital G. This is like this. G1 is components, it's Cartesian components. dx2 wedge dx3 plus cycling coefficients. So there is a majuscule G, it is defined and C, the magnetic permeability of what you J wedge dt plus rho over C is also related with the electrical properties of what you oh, no one. Sorry?
So when we put quotation marks for G is an element of two forms, so isn't B supposed to be like without the quotation marks?
No.
But how is then F an element of two forms? Because like F is.
It has a trivial answer, but you may do a lot of applications. Okay.
But so isn't F and B the same?
Okay, let me try to answer your question by doing this. Okay. When I constructed this object, it is not frame dependent anymore, but these are frame dependent. Okay. This is frame dependent. It's the Lorentzian time of an inertial observer in relativity physics. Okay? This is a true form, in quotation marks, is metric dual, is related to the electric field. But for this, we cannot say anything anymore. But I can write this as when you contract F with respect to the velocity vector field of our test particle, you get minus A. Plus E. This is this. And so you can write F as dt wedge E F plus B. But we can find A from F by this operation. This E has support on the word line of particle because we are contracting with respect to the velocity of the particle. Its trajectory is represented by this. Or we may write gamma. Previously, I have written gamma for this, but that's not important anymore. So B is F minus dt, which this is our equation. So once you know F and C, you can find B. And this is the rule in 4 dimensions. But in 3 dimensions, I have shown what's going on. Okay. So let me finish by writing. How many minutes do I have? 10? 15? 10. So, Maxwell equations for what you were in 3 dimensions. Also in Galilean point of view and also from the Lorentzian point of view, it contains all the information in it. Test particles may exhibit non-relativistic motion, so they are Galilean. They can exhibit relativistic motion. So the time is not the universal Newtonian time anymore. You have to be careful. So this is the nodal of 3 dimensions. It is not related to the connection, okay? It's related to the differential structure of the manifold out three dimensions of the instance. In system international units, okay? And GS units. These are our Maxwell equations. So, here, dimensional extension. D, 4-dimensional D, star, 4-dimensional horse star related with the Minkowski Lorentzian metric of R4. This is F, this is free-form J, and the F is 0. So, for scalar, from the scalar point of view, this is one scalar equation, to second scalar equation. There are 3, so there are 5 scalar equations. 3 more. There are 8 equations. Now we have 4 equations when we are using Gibson-Heaviside language. Now we have 2 equations when we use Cartan's language. And I will make another thing, and I will write it in just only one equation. If one knows about Clifford algebras, Clifford bundles and their minimum left ideals at every fiber, they are the Sinor species. So they are very important in physics because you use them to represent atoms in matter. Okay. Also, we use differential forms for representing Young-Mills fields. So everything is in it in some sense. So Clifford bundle-based differential geometry, smooth differential geometry, is very important, and distributional differential geometry is still progressing. Okay. Now, so you have a connection. This is the Lorentzian connection. In what sense? It preserves the Lorentzian metric. So this is the Levi-Civita connection. Levi-Civita connection of R for the metric G. G is here. Of, let's say, Minkowski space-time formulation. So the x mu, now x0 is defined as CT at an inertial track, which del x mu this is equal to Cartan's exterior derivative. Also, it is here, but then you pass to another orthonormal co-basis and basis, it will not change. Left-hand side is not dependent to the basis you used for writing the right-hand side of it. This is Cartan's exterior derivative. In terms of the connection, when can you do this? When the torsion of space-time is 0, okay? Just you may hear this, and it will be enough information at this point. And also, there is a co-derivative. It is defined with respect to the Hodge star, the inverse Hodge star, Cartan's exterior derivative, and Hodge star. And there is a map. This is an involutive automorphism of 4-dimensional manifold R4. This makes, for example, if omega is a P form, when you add eta, it will give you, if it's a P form of a manifold M, then it will multiply with this factor. So it's a scaling operation, and it's identity of identity function. So this will be, one can show that this is minus E d over dx mu nabla, sorry, not the order, the x mu tilde the, so these are known facts, but I'm not proving them here. So that's the final touch, and I will finish my lecture. Ben arkası da yazılı. Okay. So, for ease, I define if x is the one form, maybe, okay, I should say beta. Beta is a one form, and omega is any form. Yes, no. Beta is a one form for any manifold, okay? With a matrix structure. We need a matrix structure in order to define Clifford product, okay? And phi is any form. So it can be inhomogeneous. It can contain any degrees between 0 and n, if n is n-dimensional. Okay? So their Clifford product is beta dot p. This is beta wedge p plus e internal contraction with respect to the dual of beta. This was a one form, so this is a vector or a vector field. So this is the definition of Clifford product. Clifford. So there are many things that we know about Clifford algebra. Also, the topological both periods properties are belonging to these objects. Okay. So I'm writing Vx mu Clifford product nabla x. Oh, sorry. X mu and acting it to our f max plus 2 form. But note that when you put okay. One can prove that this is minus delta, not this is. Before doing that, I'd like to show you D star F is the free-form current density. Okay. So we know that H star on a P form, let's say. minus P n minus P determinant, sign of the determinant, is sign of the determinant of the matrix corresponding to the metric tensor field, the inverse acting on alpha. This is also a formula in exterior calculus on my force, okay? So we put F here. Let's put F there. So it's a 2 form, so P is 2. So N is 4. P is 2. N is 4. And we know that the sign of the determinant is minus 1. This is minus 1. So the formula reads, now reads, star F is equal to minus 1 to the power 2, 4, and there's 2. There is also a minus sign here. The inverse Hodge map, F. So, star star F is minus or star inverse F. This will be for a 2 form, okay? But this is 2 form, 2 form, 3 form. There will be a minus sign. Okay. No, I couldn't imagine. Sorry. Let's think a little bit. What can write this equation? This equation has minus delta F star first star's inverse G. I couldn't show this to you now, but I will because I didn't do it. Okay. So let's make this calculation. This is the x mu wedge del covariant derivative of the 4-dimensional manifold F plus E, say it's mu tilde del it's mu F. So this is the F minus delta F. This is also written as D slash. This is Hodge the ramp operator. Okay, the ramp. So the ramp cohomology was the subject of some part of Özgür Kerekçi's lectures. So this is flash. Okay. So it is equal to, so there is only one equation. Then you use the language of Clifford algebras or Clifford bundle-based differential geometry. But I couldn't show this. I will think on it. So this is the hand. Assignment. Are there any questions? No questions? Any questions from the Zoom? Okay, thank you.